Thank you, everyone. Hello, everyone, and thank you for being here today. So this is a presentation on the progress of this project that started in the fall in 2021. So it's not 2-year project, but it's a 1.5-year progress on the subject. So I have an abstract, but I'll go through very quickly. I present the project members. We are a multidisciplinary team. In total, there's 12 members from the GSC in Quebec City, and also from the university we are closely collaborating with, INRS. So multidisciplinary, I said, we have 6 disciplines represented, and we also had 2 PhD students that were working or still work at the moment on the project. The context of the project, as Gilles mentioned, it's about carbon capture and storage, and particularly about the geological aspect of the storage, of course. I forgot to mention that the project is under the EGP program, but the funding was provided by OERD. So sorry, it was an introductory note that I forgot. So with this project, we have the modest intention to contribute to prepare the Canadian picture for carbon capture and particularly geological storage. And what when we were preparing the project, we had the 3 components in mind: the capacity of a reservoir to store, the integrity, and the injectivity. And so with this modest project contribution with the project, we tend to go around and work on these 3 different aspects. And also what we wanted was to explore a little bit more the issue with very heterogeneous rocks, such as the carbonate ones. They are the most complicated rocks to understand and to predict the behavior of, and also low permeability carbonates as well, because most of the work that we know so far on how the reservoir will react when we try to inject CO2, or when we inject CO2, because there is a working project at the moment worldwide. All of those projects are mainly on clastic sediments, clastic rocks, and the carbonate ones are maybe the ones that are less understood at the moment. So the project has actually 3 big objectives, or we could say sub-activities, but today I will focus only on 1 and 2 because I won't have time. And it will eventually end up focusing on objective 1, but I have faith. So yeah, objective 1 is we wanted to try to end up with a protocol and a setup to inject CO2 in the rocks, and try to at the lab scale investigate what's going on. First with a more geochemical aspect, and in a second sub-activity, it was our intent was to do the same type of experiment with a slightly different setup, but trying to test geophysical tools in the meantime. And in that aspect, in that objective, in that sub-activity, we had the intention of monitoring what's going on during the experiment. I will get back on that. This is a slide that I already presented last year. It's really to illustrate how it is multidisciplinary, multi-scale, trying to do in situ as well, which is not working at the moment, and real time not working at the moment as well. But we're working on having it working, if I can say so. So yeah, this is the array of techniques and analysis that we are dealing with. Also, the project is located in, the location of the project that we use is Gaspésie, because we have one of the activity, the third one actually, is based on a quarry, a carbonate quarry exposure. But for the objective 1 and 2, our first goal was to develop our protocols and our setups, experimental setups on reference rock materials before going into the actual rocks from the carbonates from Gaspésie area. So we decided we will work on 5 different lithologies, 3 carbonate, actually 3 limestone, 1 dolomite, and 1 sandstone. The sandstone being because it was something we could compare with, because there's a lot of literature on this actual sandstone, which is a reference sandstone in North America, the Berea sandstone. The focus again is really on carbonates and low, as much as possible, eventually low permeability carbonates. So the goals for objective 1, which was the injection test with a geochemical taste, was to apply the protocol we've developed on the 5 lithologies. We wanted to work with sample saturated in brines, and we prepare brines, artificial brines that were prepared to be in equilibrium with the reservoir rock that we were studying. And we wanted to use a carbonation reactor that was available with our partner at INRS, working on pressurized and controlled temperature conditions. We were very ambitious at first. We wanted to do 2 sets of experiments for each course at 1,500 psi and 40 degrees first, which is the red arrow, and then going up and try a higher pressure, higher temperature. We ended up, you'll see, in doing something a little bit different. But the goal was to, of course, work at using the CO2 in the reactor in a supercritical condition. So yes, that's what we've done. This is the result after a 1.5 years work and progress. We managed to run 5 successful experiments. For 1 experiment for each lithology was done last fall. The setup is actually now using liquid CO2 as an input, because it was impossible to reach the condition we wanted to reach initially using gas CO2. The liquid CO2, the input as a liquid allow us to have already a working pressure that is enough, 1,000 psi as an input, and then we could put it up to 1,500 psi for the reaction. We worked at 40 degrees for 7 days. That's what we ended up doing. We tried to crank the temperature up, so we will observe more reaction. That's what we decided after a lot of trial and errors, of course. So the experiment was successful. We managed to have pre and post micro CT imaging. The brine were collected after all reaction, and it's analyzed or being analyzed. There is some precipitate sometimes associated with the brine. Those precipitates, or a solid phase, were also collected. Some of them were not in a sufficient amount to be analyzed as a petrographic output, but some of them will be. We compare the porosity and the permeability measurement on the rocks before and after the reaction, and we have a set of petrographic analysis and a set of geochemical analysis done on all aspects of the reaction: the rocks, the brines, and the precipitates. This is a quick slide also to illustrate that once the rock was in the reactor, it was actually half immersed in the brine. You have the red line that illustrates where was the transition. So the bottom of the rocks was saturated with the brine, and the top of the rocks was not bathing in the brine, but we could imagine that it was reacting with CO2 as well. And we had 3 thin sections made for each lithology, one as a radial section in the middle, hoping to catch changes on the border of the core, and also hoping to catch something going on at the interface between the brine saturated zone and the brine free zone, and also 2 thin sections of half actually disc on the top and on the bottom of the rocks. That's the thin section we are working. We have to work with. Next, okay, so quick results for 3 of the lithology in images here on the right hand side, and on the left, I will start with that actually. I put the graph to compare the porosity and the permeability before and after, to show you that there is not much change, but there is change, and we have a tendency to see a decrease in porosity after the reaction, and the permeability is not moving that much. But what's interesting is that there's definitely rocks that seems to be more reactive. They have a bigger change in porosity when we compare the porosity that is evaluated using a conventional method. So the gas porosimetry was done here. Now I'm going back to the right-hand side where I have some micro-CT imaging. It's axial section through the rocks. And what we can see for these 3 lithology is that we have the first image before the reaction. The rock was imaged before the reaction in a dry state. Then it was the same was done with the rock after the reaction, also put in a dry state. So the rocks went through the reaction for 7 days. It went out. We dried it the same way we dried the initial core plug, and then it was micro-CT scanned. And on the last column, you have the subtraction. So the 2 sets of images in 3D were compared to each other and subtracted. And you have a color bar scale, a color scale that illustrate the changes. And for those 3, there is no much changes, but that's what it is. I have another image going up. This is to illustrate that with the micro-CT imaging, we still have issue. The image I pull up is an axial section through the rock from top to bottom. It's for the Indiana limestone that I put the image on. And so you have the first is the dry one before reaction. The second image is this dry one also after the reaction. And then you have the subtraction, and you could see all those laminations that appear and that are not real. So these are artifacts, and we do have issue with the reconstruction, and this is something that needs to be worked on at the moment. But I pull up this illustration to show that with what we have, and there's not going to be a big change, we do not see a zonation of reaction from the outside to the inside of the rock, which we were expecting. And regarding the interface with the brine saturated zone and the free the zone that is free from brine, it's hard to say because we have a lot of artifacts. So we also have artifacts that you can see on the barrier sandstone on the right hand side that are called ring artifact, and they are not real as well. So there's a lot of work that is still to be done on the micro-CT imaging. That being said, we can see things and say something about what's going on with the 2 other lithology that I have. The first one being the Indiana limestone. So this one is pretty common limestone in North America. It's coarse grain, bioclastic limestone. All of the grains are basically old bioclast or bioclast fragments. The grains are cemented with pyrite, the large white arrow you can see here, and more here. Or sometimes you have a matrix, a sedimentary matrix filling the space between the bioclast, the grains. So this is a common limestone. It's pretty porous to begin with, and that's where we had. When we look at the imaging, the micro-CT imaging, you can see it after the subtraction with the cross-section, images on the bottom, that we do have changes, and we have apparently a lot of density loss. So we subtract the before and after, and we end up with the amount of the color bar illustrates the amount of changes that happen, and it's a change in density from before the reaction to after the reaction. which is consistent actually when we look at the thin section of the Indiana limestone before the reaction. We can actually see, even if it's only a reaction that was taking place for 7 days, we do have evidence of dissolution. For the Indiana limestone, there is 2 types of small-scale dissolution that seems to be occurring. Some of them are interparticle in between the rocks, so they take place here, where on the left, before reaction, you have a large calcite crystal that fill the space. After that reaction, those spaces between the particles seems to be leached. They've been attacked somehow, and we end up creating voids, so new porosity. There's also those type of reaction inside the particles. This is the second arrow on the top, and those area, the black little circles are actually the epoxy that made when they film the rock with epoxy before they cut it to make a thin section. There's sometimes there's a lot of hair that is trapped inside, and this is what you can see. So this is how you can locate all the new, well, all the holes, the pores. Some of them were already existing in the rock before, but we believe some of them, like these ones, or this one here, are newly formed.
Ça va être le temps de conclure, Stéphanie.
Okay. Whoops. C'était vraiment plus. Sorry. So I'm not done, as you can see, but I had a lot of nice images for the Indiana limestone, and we have the same type of feature for the dolomite as well, the Silurian dolomite limestone, dolomite sample, sorry, where in this case we have also interparticles and maybe sometimes intercrystalline porosity increased that occur, and they can be illustrated through the thin sections, and also when we compare the micro-CT imaging. So I'm going through those slides very quickly. And I'm not talking about the geophysical objective as planned. I will finish with those next steps. We have to complete the geochemical analysis on the thin section and the core plugs. We have a micro-axographic and SEM ongoing. We also, thanks to those observations that we have already, we know that where we are going to try to do clumped isotopes on the most reactive lithology. And as I told you, we have a lot of work to optimize the micro-CT imaging at the moment. And eventually, for the next year, we'll try to reproduce the experiments, working at higher temperature and higher pressure to see if we can actually obtain some similar result with the 3 lithology that did not react. So you'll have my contact here, and you can contact me anytime if you have any questions. Thank you.